Every second, 441 nuclear reactors worldwide generate electricity for 1 billion people. But here's what keeps engineers awake at night. Each reactor core operates at temperatures reaching 3,600 degrees Fahrenheit, hot enough to melt concrete, vaporize water instantly, and turn steel into liquid. The only barrier between civilization and nuclear catastrophe is a single steel vessel forged from a 600-ton ingot without a single weld. Picture the weight of 4 blue whales compressed into one seamless cylinder, standing guard over controlled atomic fire. How does humanity forge the largest single-piece objects ever created? How do engineers ensure steel survives conditions that would liquefy most metals? Stick around till the end. You'll discover why only one company on Earth can manufacture these reactor vessels, the jaw-dropping reason welds are forbidden, and the shocking truth about what happens when forging goes wrong at the atomic scale. The story begins at Japan Steel Works in Muran, Japan, the only facility worldwide capable of forging complete reactor pressure vessels from single steel ingots. This monopoly isn't marketing, it's physics. Their forging press, standing 12 stories tall and weighing 14,000 tons, generates forces equivalent to stacking 70 statues of liberty on a dinner plate. That's the mechanical advantage required to shape 600 tons of glowing steel. The facility consumes enough electricity to power 25,000 homes during forging operations. Backup generators the size of locomotive engines ensure power never interrupts mid-forge. A single unexpected cooling would create internal stresses shattering the vessel like glass. The plant operates 3 shifts daily, yet completes only 4 reactor vessels annually. Each vessel requires 8 months from raw steel to finished product. That's longer than human pregnancy, applied to metalworking requiring tolerances measured in thousands of inches across objects 30 feet tall. Next comes steel creation, where metallurgists blend iron with precise amounts of manganese, nickel, chromium, molybdenum, elements chosen for neutron resistance and high temperature strength. The recipe, classified by nuclear regulatory agencies, creates alloy capable of withstanding 50 years of continuous neutron bombardment without becoming brittle. Standard steel exposed to reactor conditions becomes fragile within months. Reactor-grade steel must maintain ductility for half a century. Electric arc furnaces, consuming megawatts of power, melt 300 tons of scrap and alloys at 3,000 degrees Fahrenheit. Molten steel flows into massive ladles lined with refractory bricks capable of containing liquid metal without dissolving. Workers add deoxidizers and desulfurizers, removing impurities at parts per million levels. Even microscopic inclusions, trapped oxides, sulfides, or air bubbles become crack initiation sites under reactor pressures exceeding 2,200 pounds per square inch. That's pressure crushing car engines like soda cans. Giant molds, assembled from water-cooled copper plates standing 20 feet tall, receive the molten pour. Liquid steel enters from bottom up through ceramic pipes, filling the mold cavity in controlled flow, taking 40 minutes. Technicians monitor fill rates continuously. Turbulence during pouring traps gas bubbles, creating voids. After filling, the ingot, now a glowing cylinder weighing 600 tons, solidifies over 72 hours under computer-controlled cooling. This cooling phase determines everything. Cool too fast, thermal stresses create internal cracks invisible to naked eyes but catastrophic under reactor operation. Cool too slow, large crystals form, weakening the structure. Thermocouples embedded throughout the mold measure temperature at 300 points simultaneously. The ingot shrinks 5 inches in diameter while cooling, enough movement to crack the mold if thermal expansion isn't calculated precisely. Workers strip the mold after 3 days, revealing a steel cylinder glowing dull red at 800 degrees. Now comes forging. the ancient art of shaping hot metal, scaled to industrial extremes. The 600-ton ingot, reheated to 2,300 degrees Fahrenheit in furnaces large as houses, glows brilliant orange. At these temperatures, steel becomes plastic, not liquid, but deformable under immense pressure. Picture clay that weighs as much as a jumbo jet. Overhead cranes operating at weight limits requiring structural reinforcement throughout the building lift the glowing ingot onto the press bed. The press ram, a solid steel cylinder 6 feet in diameter, descends with force exceeding 14,000 tons. That's pressure equivalent to balancing 30 fully loaded Boeing 747s on a car hood. Under this incomprehensible force, 600 tons of steel deforms, spreading like bread dough, forming into a thick-walled cylinder. Each press cycle compresses the ingot 3 inches, then retracts. The process repeats hundreds of times over weeks. The forging process requires balletic precision at colossal scale. After each press cycle, massive manipulators rotate the workpiece 7 degrees. Computer systems track rotation angle to within 0.1 degrees. Because uneven forging creates thickness variations leading to stress concentration, the ingot must be reshaped uniformly, ensuring wall thickness varies less than 1% across the entire vessel. This step is critical because reactor vessel integrity depends on grain structure. Each press cycle compresses and elongates metal crystals, aligning them perpendicular to stress directions. This crystallographic texture increases strength 30% over cast steel. Between press cycles, the workpiece returns to furnaces for reheating. Temperature drops to 1,800 degrees during forging, making steel too stiff to deform further. The ingot cycles between press and furnace 60 times, spending cumulative hours at extreme temperatures requiring constant atmospheric monitoring to prevent oxidation. After rough forging establishes basic geometry, precision machining begins. The forged cylinder, now weighing 450 tons after material redistribution, moves to vertical lathes with cutting surfaces 20 feet in diameter. Carbide tools, costing thousands of dollars and lasting mere hours, remove steel and continuous spiral cuts. Metal shavings, glowing red from friction heat, pile like metallic spaghetti. Picture this. Machinists target wall thickness of 8.7 inches with tolerance of plus or minus 0.05 inches. That's maintaining consistency thinner than a penny across surfaces 40 feet in circumference. Ultrasonic sensors scan continuously, creating 3-dimensional maps of wall thickness. Any thin spot becomes pressure concentration point, and at 2,200 psi operating pressure, stress concentrations cause catastrophic rupture. Modern reactors operate at pressures where even microscopic flaws propagate into fractures within microseconds once initiated. Quality control transcends normal manufacturing standards, entering realm of nuclear safety protocol. Ultrasonic inspection systems, using sound waves at frequencies beyond human hearing, detect internal flaws smaller than grains of rice. Technicians scan every cubic inch of the 450-ton vessel, searching for voids, inclusions, or crystal boundary irregularities. This inspection process alone takes 6 weeks of round-the-clock work. Next comes stress relief heat treatment at 1,100 degrees for 48 hours. This annealing process allows internal stresses from forging to dissipate through autolytic diffusion. Without stress relief, residual tensions from manufacturing cause cracks years later during operation. After heat treatment, hydrostatic pressure testing subjects the vessel to 3,300 psi, 50% beyond operating pressure. Workers flood the interior with water, then pump pressure until the vessel expands measurably. Any weakness reveals itself through leakage or deformation. Passing this test certifies the vessel can contain reactor core meltdown scenarios. This wasn't always possible. Back in 1955, early reactor vessels used welded construction, multiple curved plates joined by fusion welding. The Windscale reactor fire in Britain that year released radioactive iodine when welded seams failed under thermal stress. Investigation revealed welds created heat-affected zones where crystal structure changed, becoming brittle under neutron bombardment. The breakthrough came when Robert Withrich at Combustion Engineering proposed seamless forging in 1963. However, no forge press existed powerful enough. Japan Steelworks developed their 14,000-ton press in 1967 specifically for reactor vessels, recognizing the strategic importance. By 1975, all new reactor designs mandated seamless forgings. Today, the safety record speaks volumes. Zero pressure vessel failures in commercial reactors using forged construction. The few accidents that occurred, 3 Mile Island, Chernobyl, and Fukushima, involved cooling system failures, not vessel integrity. Those forged steel shells contain disaster, preventing far worse outcomes. Carbon emissions avoid 48 billion tons annually through nuclear power generation versus coal, equivalent to removing every car, truck, and plane from operation for 3 years. Nuclear energy costs drop 62% per kilowatt-hour versus solar with battery storage. A single reactor vessel forged today will generate electricity for 80 years, powering 3 million homes throughout its lifetime. So here's the secret promised. These vessels can't be welded because neutron radiation does something insidious to metal. It transmutes atoms. High-energy neutrons knock atoms from crystal lattice positions, creating vacancies and defects. Over decades, accumulated damage makes steel brittle. Welds, where crystal structures merge imperfectly, accumulate damage faster. The heat-affected zone becomes embrittlement accelerator. Seamless forging eliminates this Achilles heel entirely. Every atom in the vessel exists within continuous crystal structures aligned through forging. There are no boundaries to fail, no weak points to fracture. From 600-ton ingots to civilization's guardians, cycle completes. We've engineered the ultimate containment, steel vessels standing between humanity and atomic fire for generations. These aren't just industrial products, they're monuments to engineering paranoia in the best sense, over-engineering driven by understanding that failure means catastrophe. That forged steel cylinder represents humanity's ability to harness cosmic forces while building redundant safety margins into physical structures. We've learned to respect the atom's power by building cages worthy of containing it. Every second, jet engines spinning at 12,000 revolutions per minute thrust hundreds of passengers across continents. But here's what defies physics. Inside those engines, turbine blades made of nickel alloy operate at 3,000 degrees Fahrenheit, temperatures exceeding their own melting point by 200 degrees. Picture holding ice cubes in boiling water without them melting. That's the metallurgical miracle happening 35,000 feet above your head. How does metal survive temperatures that should liquefy it? How do engineers grow crystals larger than your hand from molten metal? Stick around till the end, you'll discover the jaw-dropping secret of single crystal manufacturing that eliminated metal's greatest weakness, and why a single turbine blade costs more than your car, yet lasts 20 years in literal hell. The story begins in specialized foundries where clean room standards rival semiconductor fabs. These facilities maintain air purity of less than 100 particles per cubic foot, 10,000 times cleaner than normal atmosphere. Even microscopic dust particles cause catastrophic flaws in turbine blades spinning at speeds where centrifugal forces generate stresses exceeding 70,000 pounds per square inch. That's pressure crushing steel like aluminum foil. Workers suit up in full-body cleanroom gear before entering casting halls. Inside, massive vacuum furnaces standing 2 stories tall and weighing 80 tons create environments replicating outer space. Vacuum pumps evacuate air until pressure drops to 1/1,000,000th of atmospheric pressure. At these conditions, materials behave differently. Impurities vaporize instantly. Gases trapped in metal escape, leaving behind purity impossible at normal pressure. Processing single batches costs $50,000 in electricity alone. Next comes mold preparation, where ceramic shells, think pottery on steroids, get built layer by microscopic layer. Technicians dip wax patterns shaped like turbine blades into ceramic slurry 10 times, waiting hours between coats. Each layer adds thickness thinner than human hair. After 20 days of coating and drying, workers melt wax away in autoclaves, leaving hollow ceramic molds with internal channels more complex than human circulatory systems. These molds contain passages narrower than spaghetti strands, designed to cool blades from inside during operation. Some channels measure just 0.008 of an inch across, thinner than credit cards. Manufacturing these passages requires such precision that lasers verify every dimension. One blocked cooling hole means blade failure at 300 degrees lower temperature. That's difference between safe flight and catastrophic engine disintegration at cruise altitude, scattering turbine fragments through fuselage like shrapnel.
Giant crucibles containing nickel-based superalloy. Mixtures of nickel, chromium, cobalt, aluminum, titanium, plus 6 other elements in exact proportions. Heat to 2,700 degrees Fahrenheit. Picture liquid metal glowing white like miniature stars captured in ceramic containers. This superalloy, developed through decades of research, contains more expensive elements per pound than fine jewelry. A single turbine blade uses materials costing $800 before any manufacturing begins. Robotic arms lower ceramic molds into this molten inferno with precision measured in thousandths of inches. Timing matters critically here. Pour too fast, turbulence creates defects. Too slow, metal solidifies prematurely. Furnaces tilt at exactly 2 degrees per second, filling mold cavities in 17 seconds. During this pour, metal temperature drops 300 degrees, requiring computer-controlled heating to maintain consistency. One temperature fluctuation of 5 degrees ruins the casting, wasting months of preparation.
Now comes the magic, directional solidification. The filled mold sits atop a water-cooled chill plate at 70 degrees Fahrenheit while surrounded by heating elements maintaining 2,400 degrees above. This creates the steepest temperature gradient in metallurgy, over 2,000 degrees difference across 6 inches. That's transitioning from Arctic to volcanic conditions in the space between your thumb and pinky. Slowly, incredibly slowly, a computer-controlled mechanism lowers the mold through the furnace at speeds of 6 inches per hour. Picture watching paint dry, then slowing that down tenfold. As the mold descends, metal solidifies from bottom upward in a razor-thin freezing front. This directional cooling forces crystal growth in one direction only, upward, eliminating horizontal grain boundaries where cracks normally form. The process takes 14 hours for a 4-inch blade. Rush it by even 10% and polycrystalline grains form, destroying blade strength. But here's where physics becomes art. At the mold bottom sits a grain selector, a corkscrew-shaped passage so narrow only one crystal nucleus fits through. As metal solidifies upward, countless tiny crystals form at the chill plate. They compete, growing upward like metallic trees racing toward sunlight. Most hit the spiral walls and stop. Only the perfectly aligned crystal, the one matching the spiral's orientation, passes through this metallurgical gauntlet. This step is critical because it ensures the entire blade, every atom from root to tip, belongs to one continuous crystal lattice. No grain boundaries exist anywhere. Normal metals contain millions of grain boundaries per cubic inch. Single crystal blades contain zero. Without boundaries, there are no weak spots where atoms slip past each other under stress. The crystal structure extends uninterrupted through the entire blade like a three-dimensional molecular Kevlar vest, with atoms locked in perfect geometric formation. After solidification, blades undergo solution heat treatment at 2,200 degrees Fahrenheit for 2 hours, then quench in inert gas. This locks crystal structure permanently and precipitates microscopic strengthening phases throughout the lattice. Next comes aging heat treatment, multiple cycles at precisely controlled temperatures that cause nanoscale particles to form. These particles, called gamma-prime precipitates, occupy 70% of the alloy's volume. Picture this. Imagine a three-dimensional checkerboard where hard particles pin the crystal lattice, preventing atoms from sliding. These precipitates remain stable at temperatures where other metals liquefy. They're the secret allowing nickel alloys to maintain strength at 3,000 degrees, temperatures where aluminum vaporizes, titanium melts, and even steel becomes taffy. The heat treatment process takes 96 hours of precise temperature control. Deviate by 15 degrees at any point and mechanical properties drop 40%. Coating application transforms already sophisticated blades into thermal protection systems. First, a metallic bond coat, aluminum-rich alloy, gets applied via high-velocity plasma spray at 20,000 degrees Fahrenheit. Metal particles accelerate to twice the speed of sound, impacting the blade surface with such force they cold weld instantly. This creates a rough surface for subsequent layers while providing oxidation resistance. Then comes the thermal barrier coating, yttria-stabilized zirconia ceramic, applied atom layer by atom layer using electron beam physical vapor deposition. In vacuum chambers, electron beams vaporize ceramic ingots. The vapor condenses on rotating blades, building up a coating 0.08 of an inch thick with a columnar microstructure full of microscopic pores. These pores act like thermal insulation, trapping air pockets that reduce heat transfer. The ceramic coating lowers blade temperature by 400 degrees, the difference between survival and meltdown. Modern engines couldn't exist without this coating technology. This wasn't always possible. Back in 1940, early jet engines used cast iron turbine blades lasting 20 hours before failure. Temperatures barely reached 1,400 degrees Fahrenheit. The breakthrough came when Pratt & Whitney researcher Frederick Vierling invented directional solidification in 1966, eliminating transverse grain boundaries and doubling blade life overnight. The true revolution arrived in 1982 when General Electric and Pratt & Whitney independently perfected single crystal casting. Turbine inlet temperatures jumped from 2,000 degrees to 3,000 degrees Fahrenheit, a 50% increase enabling massive efficiency gains. Modern turbofan engines achieve fuel efficiency triple that of 1960s designs. Today, advanced engines like the GE9X powering Boeing 777X aircraft operate at 3,200 degrees, with pressure ratios reaching 60-1. These engineering advances cut aviation fuel consumption by 65% per passenger mile over 50 years. Carbon emissions dropped by 12% when replacing older turbine blades with modern single crystal versions in existing engines, equivalent to removing 18 million cars annually from global fleets. Airlines save over $47 billion yearly through improved fuel efficiency. Maintenance costs drop 58% because single crystal blades last 3 times longer than conventional ones. So here's the secret promised. These blades don't actually survive above their melting point through material strength alone. They're actively cooled by air bled from the compressor, flowing through those microscopic internal channels at supersonic speeds. This cooling air, already compressed to 400 degrees Fahrenheit, seems hot by human standards, but runs ice cold compared to the 3,000-degree combustion gases outside. Combined with ceramic coatings reflecting heat like mirrors, the actual metal temperature stays below 2,000 degrees, hot enough to glow orange, but survivable. From molten metal to flying miracles, cycle completes. Single crystal turbine blades represent humanity's most sophisticated metal casting achievement. Objects where every atom's position matters, where crystal orientation determines survival, where manufacturing tolerances make computer chips look crude. We've engineered metal to survive in conditions nature never intended, creating materials that work at their physical limits. That's not just manufacturing, that's molecular architecture enabling the modern world's ability to shrink distance itself.
Every year, over 100,000 kilometers of new rails are laid across the planet. And every single one of them goes through hell first. Fire over 1,500 degrees, the crushing force of rollers, and jets of water that cut metal like glass. From scrap heap to gleaming steel, a rail's journey is like an initiation, where every step decides whether it survives or shatters under the first train. But what makes this steel so perfect that it can handle thousands of tons of pressure every day without bending or cracking? Stick around, and you'll see how the arteries that move the entire world are born. First, you gotta make the steel. A mix of scrap metal, iron ore, coke, and limestone gets dumped into the furnace, the raw ingredients for a future rail. The temperature in the blast furnace hits over 2,700 degrees Fahrenheit. That's 1,500 Celsius. Under that hellish heat, the metal turns liquid, glowing like the sun. Workers keep a close eye on the composition. Even an extra 0.1% of carbon can make the rail too brittle or too soft. After melting, the molten steel is poured into molds, metal forms that create rectangular blocks called ingots or slabs. They don't look like a rail yet, just solid bars a few meters long and over a foot wide. After pouring, each blank is cooled, but not completely. It's kept warm to reduce stress during the rolling process. This stage is the foundation for everything. If the steel comes out bad, even a perfect rolling job won't save it. So quality control here is almost a ritual. Chemists check the composition, metallurgists monitor the temperature, and automatic sensors track the cooling uniformity. Only when every single parameter is locked in does the blank move on into the fiery heart of the rolling mill. In the rolling mill, massive billets, up to 20 meters long, are heated in furnaces to over 2,200 degrees Fahrenheit, 1,200 Celsius. The metal becomes pliable, like dough, but keeps its density and strength. The hot blank is immediately fed into reversing rolling stands. These are huge machines with heavy rollers. It passes through them several times, first to reduce its thickness, then to give it the right shape. Each pass is a squeeze and stretch, gradually transforming the metal from a simple billet into a future rail with its complex profile: the head, the web, and the foot. To get the exact geometry, they use a final sizing roll. It's like the final polish of the shape, with tolerances on this step not exceeding 0.3 of a millimeter. Right after rolling, while the rails are still hot, they go through a cooling process. They're either evenly blasted with air or left to cool on an open rack. It's crucial that the cooling is symmetrical, otherwise the metal could warp. To ensure a smooth, bump-free ride at high speed, individual rails are welded into long sections, up to 400 meters without a single joint. The main method is thermite welding. In a special mold between two rails, a gap of a few millimeters is left. A molten steel mixture, created by the reaction of powdered aluminum with iron oxide, is poured in. The temperature hits a scorching 4,500 degrees Fahrenheit, 2,500 Celsius. This molten metal flows into both parts of the rail and fills the joint area. When it solidifies, it creates a monolithic bond, stronger than the rail itself. After that, the excess metal is trimmed off, and the weld is ground down to a perfectly smooth level, without a single bump. Every joint is inspected with ultrasound or eddy currents to make sure there are no hidden micro cracks. These long rails are easier to transport than you'd think. They're either wound onto special drums or carried on platforms with pivoting supports. And on the construction site, the sections are joined again, this time by welding or using special bolted joints. The result is a continuous rail line that stretches for kilometers without a single click. The same silent glide we've come to expect on high-speed trains. But first, after rolling and welding, the rails are still alive. There's stress left inside the metal, and the grain structure needs to be stabilized. This is where heat treatment comes in, giving the rail its strength, wear resistance, and durability. And it looks almost like a metallurgical spa session. The rail is rapidly heated to high temperatures, around 1800 degrees Fahrenheit, 1000 Celsius. This is done in furnaces, tens of meters long, where the temperature is controlled to the degree. At this heat, the steel's crystal lattice shifts into a new state, austenite. But the main event starts after that. The rail is instantly cooled. Jets of high-pressure water are aimed along the head and web, the very parts the wheel rolls on. The temperature drops in a flash, and a new structure forms in the metal, martensite, an extremely hard, wear-resistant phase. But to avoid brittleness, the rail is slowly heated and cooled one more time. This balances the structure, relieves any extra internal stress, and ensures the rail can handle frost, heat, and thousands of trains a day. In the end, the metal holds its shape and withstands pressures of tens of tons per square inch without deforming. Before a rail hits the road, it goes through a whole series of tough tests, like it's trying to join an army of high-speed transport. In special labs, it's checked for strength, hardness, geometry, and internal defects. First up, ultrasonic testing. High-frequency waves are sent into the rail. If there's a micro crack or void inside, the signal bounces back and flags the problem. Then, hardness measurements along its entire length to make sure the heat treatment was uniform. At the same time, its straightness and profile are checked. Laser sensors scan every inch, detecting even tiny warps that could cause vibration or wear. And finally, bend and impact tests. A piece of the rail is loaded with pressure dozens of times greater than the weight of a train to make sure it can handle any challenge on the route. When the rail has successfully passed all the tests, it's time for its most important journey, to the installation site. But how do you transport giant metal strips over 90 meters long? Regular trucks can't handle it. Here, they use special railway platforms with curved supports that reduce stress and prevent the rail from sagging or vibrating during transit. Sometimes, rails are transported already welded into even longer sections, from 400 to 600 meters. Before installation, the rails are heated or cooled depending on the ambient temperature. This is to compensate for the thermal expansion and contraction of the metal. Otherwise, it would buckle in the heat or gaps would form in the cold. In practice, each rail is laid with these physical changes in mind, usually at a stress-free temperature point.
Every year, humanity extracts over 2 billion tons of iron ore from Earth's crust. Picture this. More than half of our planet's entire weight is iron, most locked in the core, creating the magnetic field protecting all life. But here's what shocks engineers worldwide. We're standing on the most abundant metal in the universe, yet accessing it requires temperatures hotter than volcanic lava. How does rust-colored rock transform into gleaming steel skyscrapers? How do ancient mountains become modern civilization? Stick around till the end. You'll discover why iron shaped human history more than gold ever did, and the jaw-dropping secret hiding inside every bridge, car, and building around you right now. The story begins in Western Australia's Pilbara region, where iron mountains stretch across landscapes older than dinosaurs. Massive excavators, standing 8 stories tall, picture buildings that walk, tear into rust-red cliffs with bucket teeth weighing 12 tons each. These mechanical giants rip through rock layers formed 3 billion years ago when Earth's oceans first rusted. With thunderous crashes echoing across 40-mile-wide craters, each excavator loads haul trucks carrying 400 tons per trip. That's the weight of 80 elephants moving at 40 miles per hour on tires taller than basketball hoops. Processing 30 million tons annually from single mines, enough iron ore to build 12 Golden Gate bridges every single day. Next comes crushing, where house-sized jaw crushers, imagine dinosaur mouths made of hardened steel, pulverize boulders into gravel-sized chunks. With deafening roars splitting eardrums even through protection, these crushers generate forces exceeding 20,000 pounds per square inch. Clouds of red dust billowing upward create artificial sunsets visible from space satellites. Conveyor belts stretching 12 miles long, longer than Manhattan, transport crushed ore at 18 miles per hour. Workers riding inspection carts traverse distances requiring 25 minutes one way. That's enough belt to wrap around 300 football fields. Every hour, 50,000 tons flow through this system, weight equivalent to 5 Eiffel Towers moving continuously past checkpoints. Giant grinding mills, standing 5 stories tall, with diameters matching Olympic swimming pool widths, pulverize rock into fine powder. Inside these rotating drums, 20-ton steel balls, each weighing more than shipping containers, tumble with ore, creating grinding thunder heard miles away. Operators monitor vibrations. Wrong frequencies mean catastrophic bearing failures, costing millions. At rotation speeds creating gravitational forces triple normal Earth gravity, particles shrink to powder finer than talcum. Processing 8,000 tons hourly, that's filling semi-truck after semi-truck every 30 seconds. This powder, called concentrate, contains 65% iron. Magnetic separators then extract iron particles using forces strong enough to levitate railroad spikes, leaving waste rock behind. Next comes the blast furnace, a towering inferno standing 30 stories high, its steel shell glowing dull orange even from outside. At internal temperatures exceeding 3,000 degrees Fahrenheit, hot enough to vaporize aluminum instantly, iron ore transforms into liquid metal. Picture Dante's Inferno engineered with precision. Measured charges of iron ore, coke, and limestone descend from the top, while superheated air blasts upward at 2,000 degrees from ring-shaped nozzles called tuyeres. This creates a raging chemical storm, where carbon monoxide rips oxygen from iron oxide molecules. The reaction releases enough heat to melt granite. Every 3 minutes, sensors check 20 different parameters. Without precision, furnaces explode with force demolishing city blocks. The blast furnace operates continuously for 15 years, never cooling, never stopping, like Earth's core relocated to industrial facilities. Inside this chemical reactor, materials descend through distinct zones. Upper regions preheat incoming ore. Middle zones drive off moisture and carbon dioxide. Lower depths become hell itself, where iron liquefies. At the hearth bottom, molten iron collects at 2,800 degrees Fahrenheit, dense as lead but flowing like water. Every 4 hours, workers drill through clay-plugged tap holes. Liquid iron erupts in blinding white rivers, flowing through ceramic channels into railroad cars holding 300 tons each. This step is critical because timing determines metal purity. Tap too early, slag contaminates. Too late, furnace pressure ruptures containment walls. After tapping, slag, lighter impurities floating atop molten iron, gets diverted into separate channels. This glowing amber liquid, essentially liquefied rock, contains calcium, silicon, and aluminum oxides stripped from ore. Rather than waste, it becomes roadbed material and cement ingredient recycled at 98% rates globally. The molten iron, called pig iron, contains 4% carbon, too brittle for construction. Picture glass that looks metallic. Drop pig iron from waist height, it shatters into fragments. Next comes the basic oxygen furnace, where pure oxygen blasted at supersonic speeds through 3-foot diameter lances burns away excess carbon in 17 minutes. Flames shooting 70 feet high, temperatures hitting 3,200 degrees, create hurricane-force winds inside steel vessels holding 350 tons of liquid metal. Steel making requires precision rivaling brain surgery. Computer-controlled oxygen flow adjusts by milliseconds. Operators add exact amounts of manganese, silicon, chromium, elements changing steel properties dramatically. Too much carbon, steel cracks in winter cold. Too little, metal bends under load. Picture this: alloying elements get injected via submerged lances. Electromagnetic stirring, invisible but powerful, homogenizes composition. Samples extracted every 3 minutes get analyzed via spectrometers, determining chemistry within seconds. Modern furnaces achieve carbon content accuracy to 0.01%, difference between skyscraper standing or collapsing. After refining, liquid steel flows into continuous casting machines producing slabs 30 feet long, weighing 25 tons at rates of 1 slab every 90 seconds. This wasn't always so advanced. Back in ancient Anatolia around 1300 BC, Hittite metallurgists discovered heating iron ore with charcoal produced workable metal. That breakthrough, accidental furnace conditions reaching iron's melting point, changed human civilization forever. Iron tools outperformed bronze, enabling agriculture revolution. The breakthrough came when British inventor Henry Bessemer patented his converter in 1856, slashing steel production time from 24 hours to 17 minutes. Suddenly, steel costs dropped 90%. This single invention built modern cities. Skyscrapers, bridges, railroads exploded across continents. Today, global steel production exceeds 1.9 billion tons annually. That's enough to build 75,000 Eiffel Towers yearly, or manufacture 43 million automobiles, or construct bridges connecting every coastline on Earth. Carbon emissions drop by 62% when using recycled steel versus virgin ore, equivalent to removing 12 million cars annually. Industry saves over $80 billion yearly through scrap recycling. Processing costs drop 43% because melting scrap requires 1/3 the energy of blast furnaces. So here's the secret promised. Every ton of steel you see, bridges, buildings, cars, will be recycled indefinitely. Unlike plastic decomposing into microparticles or paper pulping into mush, steel never degrades. Magnetic separation extracts it perfectly from demolished structures. That girder in your office building might contain steel from 1930s locomotives. Your car's frame could include battleship armor from World War II. Nothing disappears. Metal merely transforms, reborn eternally. From ancient mountains to modern marvels, cycle completes. Iron, humanity's most essential metal, circulates through civilization like blood through veins. We're not consuming Earth's iron, we're borrowing it, briefly, before passing it forward to futures we'll never see.
Every year, the world produces over 130 million tons of glass. But few people know that behind every clear window, bottle, or skyscraper facade lies a true symphony of fire, air, and light. Imagine a river of molten sand flowing over a mirror of tin, giving birth to perfectly flat sheets of glass so smooth they can reflect the clouds. But there's another kind of glass, one that's alive, with a soul, created by the breath of a craftsman and the fire of a furnace. Stick around to the end, and you'll see how ordinary sand travels through a 3,000-degree journey to become the transparent marvel our world is made of. While the vast majority of architectural glass today is born from a perfectly flat, fiery river flowing over molten tin in the float process, the true soul of the material is revealed in the methods that give it character and uniqueness. This journey from a simple, transparent sheet to a work of decorative art is a fascinating one. To create glass with individuality that carries the mark of a human touch, craftsmen still turn to techniques that have existed for centuries. A glassblower dips his long, hollow pipe into a furnace where a mass of sand and other minerals boils at 2000 degrees Fahrenheit. He gathers a honey-like ball of glowing glass on the end of the pipe and, skillfully rotating it, begins to blow air into it. The initial bubble, born from his breath, gradually transforms into an elongated, shining hollow cylinder. Thanks to the force of gravity and skillful swinging, this cylinder can reach several feet in length. After the ends of the cylinder are cut off, it's sliced lengthwise and placed back in the furnace. There, under the heat, it slowly unrolls like a scroll, and the craftsmen smooth it into a flat sheet. Glass born this way is never perfectly flat. It's alive, retaining subtle waves, tiny air bubbles, and fine lines that tell the story of its fiery birth. This glass has a watery, organic quality that can't be replicated by a machine. But the creation of unique glass doesn't stop at forming the sheet itself. Other methods transform ordinary sheets into complex decorative elements. Fusing allows artists to literally paint with glass. Different colored pieces of glass are arranged on a base sheet and sent into a kiln, where at 1500 degrees Fahrenheit, they melt together into a single piece, creating bright, painting-like compositions. Closely related is the process of slumping, or bending, where a flat sheet of glass is heated until it becomes soft and sags under its own weight, taking the shape of a ceramic or metal mold placed beneath it. This allows for the creation of curved panels and three-dimensional glass sculptures. Modern technologies add even more possibilities. Lamination allows for baking colored films, fabrics, or even thin sheets of metal between two layers of glass, creating endless variations of color and texture. Sandblasting and chemical etching remove the top layer of glass, making it matte and creating intricate patterns on its surface, from simple geometric shapes to photorealistic images. In this way, by combining ancient crafts with cutting-edge technology, modern production transforms simple glass into an expressive architectural material capable of shaping light, color, and space. In today's world, where tons of used glass containers are collected daily, the journey from the recycling bin to a new bottle isn't just remelting. It's a high-tech odyssey driven by computers and light. Imagine a mountain of crushed glass, dozens of feet high, where clear, green, and brown shards are mixed with labels, caps, and ceramic contaminants. Turning this chaos into pure raw material is a job for a whole complex of smart machines. It all starts with mechanical crushing, where steel hammers turn bottles and jars into fragments a few inches in size. This stream of glass, like a moving river, embarks on a journey through a labyrinth of sorting systems. First, powerful magnetic separators pull out any steel contaminants, and then eddy current systems literally shoot aluminum caps and foil into separate containers. Powerful blasts of air blow away light paper labels and plastic residue. But the hardest task is yet to come. Removing impurities that are almost identical to glass in weight and size, like pieces of ceramic, stone, or porcelain. These enemies of glass don't melt at standard temperatures and turn into defects in new products, so their removal is critically important. This is where optical sorting comes into play. The glass fragments are accelerated on a conveyor belt to high speed and fly through a scanning zone. For a split second, each fragment is illuminated by a bright light, and high-speed cameras take hundreds of pictures. A computer system, with lightning speed, analyzes the images, identifying foreign bodies by their transparency, structure, and shape. As soon as the system spots an opaque piece of ceramic, it instantly calculates its trajectory and commands a battery of air jets. A precise, sniper-like puff of compressed air knocks the unwanted element out of the mainstream, sending it to waste. This process is repeated thousands of times a minute. At the same time, an equally important sorting by color takes place. The same optical systems analyze the spectrum of light passing through each fragment. The machine distinguishes between crystal clear, rich green, and deep brown glass. Depending on the set program, the system can, for example, select only clear glass, knocking out all colored fragments with air jets, or separate the stream into 3 distinct color fractions. The result is a perfectly clean, color-sorted raw material, cullet, ready for a new life without any loss of quality, which is the pinnacle of the modern circular economy. This raw material can then be used to make flat glass. The birth of modern flat glass is a symphony of fire and precision, a spectacular process that turns ordinary raw materials into perfectly transparent sheets. It all begins in a massive melting furnace, the fiery heart of the plant that runs continuously for years. Into this furnace, which resembles a lake of molten fire, a carefully measured mix, or batch, is loaded, consisting of pure quartz sand, soda ash to lower the melting temperature, and limestone for stability. A significant amount of cullet, or crushed recycled glass, is added to this to help speed up the melting process. Inside the furnace, at hellish temperatures approaching 3,000 degrees Fahrenheit, these solid components slowly transform into a uniform, viscous liquid. The melting process is strictly controlled to ensure all particles are completely dissolved and gas bubbles are removed, creating a flawlessly pure melt. From the furnace, this stream of glowing orange molten glass, resembling a river of lava, flows smoothly into a bath of molten tin. This is the culmination of the process known as the float process. The tin bath, stretching for hundreds of feet, has a perfectly smooth, mirror-like surface. Since glass is lighter than tin and doesn't mix with it, it spreads out over the surface, forming a perfectly flat ribbon of uniform thickness. Gravity levels it from the bottom, and surface tension smooths it from the top, creating impeccable optical quality. The speed at which this ribbon is pulled from the bath determines its final thickness with pinpoint accuracy. After forming a perfectly flat surface, the glass ribbon, still very hot but now solid enough to hold its shape, enters the calmest but most critical stage, annealing. It enters a long tunnel known as an annealing layer. If glass is cooled too quickly, its surface will contract faster than its interior, leading to massive internal stresses that will make it brittle and prone to shattering. In the layer, however, the glass temperature is slowly and controllably reduced over several hundred feet, from over 1,000 degrees down to room temperature. This process allows the entire sheet, both surface and core, to cool evenly, relieving all internal stresses. From the other end of the layer emerges a single, flawless, continuous ribbon of perfectly transparent, stress-free glass, ready for automatic cutting into huge sheets that will become the windows, facades, and doors of our world. Every year, the world lays down over 1 billion tons of asphalt, the material that modern civilization would literally grind to a halt without. But few people know that every foot of road is the result of a complex alchemy of stone, fire, and oil. It all starts with an explosion in a quarry and ends with a hot, black mass steaming under the wheels of a roller. In this video, you'll see how asphalt is born, from blasting rock to the final roller that polishes a new road. And if you stick around to the end, you'll learn a secret that most drivers don't even know exists. Almost nothing goes to waste. That crushed old asphalt is then added to the new mix back at the plant. On average, new asphalt laid on our roads contains about 22% recycled material. The payoff here is huge, both economically and for the environment. First, it drastically cuts down on the need to quarry new stone and produce new bitumen, which saves natural resources and energy. Second, it makes the final product cheaper, saving billions of dollars from road maintenance budgets. So, every car trip you take is a journey on a complex piece of engineering that not only withstands massive loads, but is also a prime example of an industrial ecosystem where the old is constantly reborn into the new, closing the loop and making the country's infrastructure a little more sustainable. The story of asphalt doesn't start on the road. It starts in 2 completely different places. The first is a quarry. It's a massive wound on the face of the earth where rock is blasted out. It all begins with a loud explosion that shakes the ground for miles. Huge boulders break away from the rock face. Then, giant haul trucks with wheels taller than a person move in and haul these stone boulders to the primary crusher. This is a metal monster that crushes massive boulders into smaller chunks with its steel jaws and incredible force. But that's just the beginning. The stone then goes through a whole series of crushers and screens, giant vibrating sieves. The goal isn't just to crush the rock, but to carefully sort it by size. The result is entire mountains of clean, sorted stone, which we call aggregate. You've got everything here. From large, fist-sized rocks to fine crumbs and even dust, like sand. Each size is stored in its own separate pile. It's like in your kitchen, where you have flour, sugar, and salt, each ingredient separate, waiting for its turn. This is the skeleton of the future asphalt, making up 95% of its mass. The second place where asphalt is born is an oil refinery. When crude oil is processed into gasoline, diesel, jet fuel, and other light products, a thick, black, viscous substance is left at the very bottom of the distillation tower. This is bitumen. In its normal state, at room temperature, it's as hard as a rock. You can shatter it with a hammer. But if you heat it up, it becomes a liquid, like thick syrup. It's this property, being solid when cold and liquid when hot, that makes it the perfect glue for our stone skeleton. Bitumen is the soul of asphalt. It's black heart that holds everything together. Now, let's head over to the asphalt plant. This is where all the ingredients come together. From a distance, it looks like a complex tangled metal jungle. Tall silos, endless conveyor belts, pipes, tanks, and a central tower with smoke rising from it. It's a real factory that works like a single, well-oiled machine. Different sizes of aggregate are fed from separate bins onto a conveyor belt. But not just randomly. The whole process is controlled by a computer. An operator in a control booth inputs the exact recipe for the asphalt. Depending on where it's going to be used, a busy highway or a quiet side street, the recipe will be different. The computer knows exactly what percentage of large stone, medium, small, and dust is needed for the perfect mix. It's like baking a complex cake, where every gram counts. This mix of stones begins its journey up a long, inclined conveyor and enters the heart of the plant, the drying drum. This is a huge, long tube that slowly rotates, set at a slight angle. From one end, a powerful burner blasts a roaring pillar of fire inside, like a jet engine. The temperature inside hits 300 degrees Fahrenheit. The stone, slowly tumbling inside this drum, heats up, and most importantly, gets completely dried out. Moisture is the #1 enemy of good asphalt. Even a single drop of water can prevent the bitumen from sticking properly to the stone's surface. So, the stone has to be bone dry. After the drying drum, the hot, moisture-free stone is carried up by an elevator to the very top of the central tower. There, it passes through another set of screens for a final quality check on the sorting, and then falls into hot storage bins. Meanwhile, in special insulated tanks, our black glue, the bitumen, is being heated up. It's also brought to a high temperature to make it fluid and runny. And now comes the climax. The computer gives another command. A wayhopper, with incredible accuracy, measures out the required amount of hot stone of each size from the different bins. Then, a precisely measured amount of hot liquid bitumen is sprayed into this superheated stone mix. This entire mass, stone and bitumen, is dropped into a mixing chamber, called a pug mill. It's like a giant kitchen mixer, but instead of whisks, it has 2 powerful shafts with metal paddles. These paddles churn the hot mass with enormous force, and in less than a minute, every single stone, every grain of sand, is coated in a thin, shiny film of black bitumen. Out of the chamber comes the finished asphalt, a uniform, steaming black mass with a characteristic oily smell. Now this hot, freshly made product needs to be stored until it's shipped out. It's lifted and dumped into special insulated storage silos. They're like giant thermoses that can keep the asphalt hot for many hours, sometimes even days. Dump trucks pull up under these silos. With a loud clang, a gate opens and several tons of hot asphalt pour into the truck's bed with a roar and a cloud of steam. The bed is always covered with a tarp to keep that precious heat in during transport to the paving site. At the construction site, the final act begins. The dump truck slowly unloads the hot mix into the hopper of a special machine, an asphalt paver. This machine, moving forward slowly, evenly spreads the asphalt over the road surface, forming a perfectly level layer of a specific thickness. At the back of the paver is a heavy, heated plate called a screed. It does the initial compaction and gives the surface its first pass of smoothness, but the asphalt is still soft and loose. To make it strong, it needs to be compacted. Right behind the paver follows a whole team of heavy road rollers. First come the large steel drum rollers, which use their immense pressure to squeeze the air out of the asphalt mix and force the stones to lock together tightly. Then, pneumatic tire rollers might be used, which knead the surface, making it even denser. And in the final stage, smooth steel drum rollers pass over it again to give the road its final, smooth finish. As the asphalt cools, the bitumen turns from a liquid back into a solid. It permanently glues all the stones together, turning the loose mix into a strong, waterproof monolith. After a few hours, the road that was recently hot and soft becomes hard and ready for traffic. And that's the whole point. From the explosion in the quarry to the heavy roller on the road, every stage of this process is designed to create a durable, reliable surface that will withstand thousands of cars every single day.